So in the previous video, I talked about how you embed inputs before passing to the model. In fact, before doing that, you'd have to do another pre-processing stuff to that embedded tokens. It's called positional encoding. It would add information about sequence of order of sequence to the model, since the transformer do not inherit sense of the order of the inputs or tokens like RNNs or CNNs. In RNNs, they have sense of the order because they process inputs sequentially. So if the input was word "I like playing tennis on Sunday," before, so these X would be "I like playing tennis." When processing the word "playing," you'd have to process "I like" beforehand before processing the word "playing," in order to acquire hidden states computed when processing the word "I" and "like." So by this method in RNNs, they know the order of tokens or inputs, whether it's in text or numerical values, like used for stock price data sets. So they know the word "I" comes before "like," and "like" comes before after the "I," and so on. But since in transformer model they started training in parallel, they lose sense of the order. So they don't know in which order that each tokens are. Like the model doesn't know positions for each tokens. The full RNNs, they know like the position of the word. I don't know if RNNs captures each positions for each words like this, but this transformer model doesn't know the positions, whether it's relative or absolute for tokens. So yeah, and how does it implemented? I mean, how does it work? They use sinusoidal functions, sine and cosine, because sine are even and cosine are odd. So for even indexes, sine functions are used, and for odd indexes, cosine functions are used. By the way, these are not embedded matrix, but so when we are doing this, first we just create matrix. We just create it's just literally the function same as function names, but we create matrix that encodes positions for each words, and we add that to the embedded tokens matrix, which were created in embedding layer, and we pass the result to the model, which would start the training process. So we have to create matrix. So what do? We loop through number of sequence length. For this example, I set it to 6, and for the dimension model for 6 as well. This dimension model is same as embedding dimension. You set it to create embedding matrix. It has to be same because you are adding to embedding matrix later. So we go through the loop. First, we have to create a denominator, which would be used here. It's 10,000 to the 2 divided by indexes divided by dimension. So this word I all corresponds to here because position is 0. I means first word. So the first dimension for first word, because it's even indexes, this is index 0. So, and for word 0, we use sign function, position 0, and the denominator is 1 for this. And for next dimension for this word, because it's odd index, we use cosine, and it's still the denominator is still 1. And for this, the denominator would be changed. The new denominator, and so on. And for this word, it would be, for this I, the vector would be 0, 1, 0, 1, 0, 1. It would look like this. So this is for word I. And when we look at cosine and sine function, when it is, so this is sine of 0, it would be here. Sine of 0 would be 0, cosine of 0 would be 1, another sine of 0, cosine of 0, sine of 0, cosine of 0. So it would just truncate between sine 0 and 1. And because, no matter how, so this sentence has sequence length of 6, even if you had 100 or 500, the first vector would be 0, 1, 0, 1, no matter how big your sequence lengths are. And next, the word like corresponds to this one. The sign of 1 would be this. Sign of 1 would be around here, 0.84. And cosine of 1 would be around here. So 0.54. And we just keep doing that, and this will be 0.04. So sine of 0.04 will be around here. So it's 0.04, and cosine of 0.04 will be around here. And for the next two dimensions, the values passed to this sine and cosine function will be smaller than this one. So the output will be even smaller. It gets closer to this axis. So that's how this positional encoding encodes positions for each tokens. And when the sequence length for this example I used 6, if the sequence length was like 100, we would have sine and cosine function that have more frequencies with shorter wavelength. So we'd pick or encode each positions for each tokens using different frequencies, so that positions for each tokens never wrap or overlap. So yeah, this is really mathematic, even though I'm doing AI stuff. I mean, there are a bunch of math equations involved in AI, but yeah, I would like to explain more deeply once I understood clearly, but this is as far as I could explain. This encodes positions for each tokens using different frequencies. So this denominator ensures different frequency scales across dimension. This is this is how, like I just said. So I think this is it for today's video, and next video I think I would like to explain about multi-head attention, which is like a core component for the model. Yeah, until then, thanks.